The ventral tegmental area, VTA, is a crucial part of the brain's reward system, playing a key role in motivation, pleasure, addiction, and reinforcement learning. Here's a deep neurological breakdown of the VTA, covering its structure, function, and neurochemical interactions. Overview of the VTA. The ventral tegmental area, VTA, is a small group of dopaminergic neurons that produce dopamine, located in the midbrain near the substantia nigra. It is involved in reward, reinforcement, motivation, learning, addiction, and mood regulation. The VTA is part of the mesolimbic dopamine system, which is crucial for experiencing pleasure and motivation. Anatomical structure. The VTA is located in the midbrain, specifically in the tegmentum, which is the floor of the midbrain. It has dopaminergic, GABAergic, and glutamatergic neurons. Dopaminergic neurons, DA neurons, send dopamine to various parts of the brain. GABAergic neurons, inhibitory neurons that regulate dopamine release. Glutamatergic neurons, excitatory neurons that modulate activity. Major connections, afferents and efferents. Inputs to the VTA. Prefrontal cortex, PFC, sends glutamatergic input, excitatory, that regulates reward seeking. Lateral hypothalamus, LH, modulates feeding and reward. Bed nucleus of the stria terminalis, BNST, regulates stress responses. Lateral habenula, LHB, sends inhibitory signals, dampening reward-related responses. Outputs from the VTA. Nucleus accumbens, NAC, part of the striatum, drives motivation, reinforcement, and addiction behaviors. Prefrontal cortex, PFC, regulates decision-making and executive control. Amygdala processes emotions, especially fear and reward. Hippocampus, involved in memory and learning related to rewards. Neurotransmitters in the VTA. The VTA is primarily known for dopamine, but it also involves GABA and glutamate. Dopamine, DA. The VTA is one of the major dopamine-producing centers in the brain. Dopamine projection pathways. Mesolimbic pathway, VTA, nucleus accumbens, NAC, reward, addiction, and motivation. Mesocortical pathway, VTA, prefrontal cortex, PFC, decision-making, executive function. Mesostriatal pathway, less prominent in VTA, motor control. B-GABA, gamma-aminobutyric acid, inhibitory neurotransmitter that regulates dopamine release. Local GABAergic interneurons within the VTA help control overactive dopamine firing. C. Glutamate. Some neurons in the VTA release glutamate, which can excite other neurons in the reward pathway. Role of the VTA in neurological functions. A. Reward and motivation. The VTA is activated when experiencing pleasurable activities, for example, eating, socializing, sex, drugs, music. Dopamine release in the nucleus accumbens reinforces behaviors, making them more likely to be repeated. It also plays a role in effort-based motivation, influencing how much effort a person is willing to put into a task. B. Learning and memory. Dopamine signals from the VTA influence reinforcement learning. Positive reinforcement. When a reward is received, dopamine levels increase. Negative reinforcement. If an expected reward is absent, dopamine levels decrease. The VTA interacts with the hippocampus to encode reward-related memories. C. Addiction and substance use. Drugs like cocaine, amphetamines, nicotine, alcohol, and opioids hijack the VTA's dopamine system. Mechanism. Many drugs increase dopamine release from the VTA into the nucleus accumbens, creating intense feelings of pleasure. Over time, this leads to dopamine receptor downregulation, making natural rewards less pleasurable and increasing drug-seeking behavior. Withdrawal symptoms occur when the VTA fails to produce normal dopamine levels without the drug. D. Depression and mood disorders. Reduced VTA activity is linked to anhedonia, inability to feel pleasure, a key symptom of depression. Chronic stress inhibits the VTA, leading to dopaminergic dysfunction and lower motivation. Antidepressants, like SSRIs, may indirectly affect VTA dopamine regulation. E. Anxiety and fear. The VTA modulates anxiety via dopamine projections to the amygdala. It is involved in fear learning, helping the brain evaluate whether a situation is safe or threatening. F. Schizophrenia and psychosis. Overactive VTA dopamine signaling in the mesolimbic pathway is associated with hallucinations and delusions. Antipsychotic medications work by blocking dopamine D2 receptors, reducing excessive dopamine activity. VTA and brain plasticity. The VTA plays a role in synaptic plasticity, helping the brain adapt and form new connections based on experiences. LTP, long-term potentiation, in VTA neurons strengthens reward-related learning. Neurogenesis and adaptation. Chronic drug use, stress, or enriched environments can reshape VTA circuits. VTA and neuromodulation, brain stimulation. Deep brain stimulation, DBS, of the VTA is being explored as a treatment for depression, addiction, and Parkinson's disease. Optogenetics. Scientists can selectively activate or inhibit VTA neurons in animals to study reward-seeking behavior. Summary. The VTA is a dopamine hub that influences reward, motivation, learning, addiction, and mood. It connects to the nucleus accumbens, prefrontal cortex, amygdala, and hippocampus, forming the brain's reward circuit. Dopamine release from the VTA drives motivation and reinforcement learning. Dysfunction in the VTA is linked to addiction, depression, schizophrenia, and other neuropsychiatric disorders.